Thank you, Laura, for the generous introduction. I want to thank the Wang family for the generous endowment and for making these lectures possible. To Jeff Ban, my host in the Civil Engineering Department, for the amazing logistics of the whole visit. And it's really nice to see old friends and good friends in the audience, and Don, Lily, and many others. Today, I'm going to talk about inference and control in routing games. That might sound a bit of an abstract title, but it's actually very practical, and we'll try to juggle back and forth between some theory and some practice, and hopefully you'll connect with many of the themes, because many of you were stuck in traffic today, will be stuck in traffic next week going to Thanksgiving dinner, so we should all prepare collectively for this. So first, I'm going to go through a general framework for traffic operations, which is kind of the underlying backbone of the work we do. And then I'm going to talk about two specific problems. Inference problems, which is how you find out what traffic is like and what you do about it. And then games, which is something that, as you will find out through the lecture, we all play willingly or not, knowingly or not, but that we're all part of. So this is the diagram that undergrads taking any control theory or any optimization class probably go through in their first lecture. And this is a very good representation of, if you think, any system that is controlled with sensors and actuators works. There's a plant which has a system, whether it's an airplane, a car, the road, or anything. There's sensor actuators, and then there's a controller to control it. And what I'd like to do is try to think about the transportation system in these terms, which will set up the stage for the rest of the talk. So at the core of the system is a dynamics, which is how the system physically works. So think about next week when you're going to your Thanksgiving dinner. Unless you leave really early, that's the type of traffic you will experience. This is last year's Thanksgiving traffic in LA. And I'm sure you could generate similar videos pretty close to wherever you live. So the point here is that to model something like this, you know, it's not that easy. There's lots of nonlinear phenomena that happen, and there's decades and decades of work. Generations and generations of traffic engineers have spent a lot of time trying to understand the physics of how these systems evolve. And so if you understand that to a certain level, in a sense, you have a good understanding of how the system works. And so now, just like any control system, you need to understand how to sense it. You might have a good understanding of how it works, but you need to understand what it's doing. And if you think about sensing infrastructure around you, you're probably familiar with this type of technology. First, it's not very elaborate, and second, there's not much of it. Whether these are loop detectors, whether these are cameras, whether these are radars, fast track, tubes, anything you name it, these are mostly historically tools which have been developed and deployed by public agencies. And at most, maybe 10% of the road is instrumented with it. So there's very little data, if you will, to measure traffic. On the control side, to control the system, it's not that different. I mean, if you think of yourself in your car in the morning, where are you going to be, quote, controlled? I mean, there's traffic lights, there's tolling, which might have meterings. There's metering at the on-ramps and the off-ramps. There's some restricted access lanes, the 405 here being one example with the tolling, maybe some ways to give you more information, and that's pretty much it. And even if you take a corridor like the 210 in California, so this is one of the test beds that we're working on with the California DOT, I mean, think of this corridor, which is probably 20 kilometers, and there's 450 assets on this corridor to control traffic. Every day, there's hundreds of thousands of people going through this corridor, and you have 450 control points to control this entire flow of people. That's very little. And this is the reality of transportation engineering for the last half century. For the last half century, this has been the only way at the disposal of public agencies to control your mobility, which is to make you flow better from wherever you live to wherever you work or wherever you want to go throughout the day. And so that upper box, in a sense, this is like a 2 minutes summary of the way that upper box works. Now you can wonder what's under the hood, like all these traffic lights, all this urban infrastructure I see, how does it work? And here's another 2 minutes description of how it works. At the simple level, you have state estimation and demand forecast. State estimation is the process of trying to collect whatever data you have and reconstruct the most likely state of the system given the data you have. So you can think about it as a dashboard that is essentially empowering a traffic engineer in a command center somewhere to make these decisions. And so to understand traffic, engineers have simple representation tools called time-space diagrams, where in a 2D diagram you plot time and space, and the color level encodes the speed of the traffic. And so that color level fills up throughout the day, and if you look at what it looks like now, that gives you a depiction of the way traffic flows on a lane of freeway. And then you have demand, and demand forecast, which is essentially trying to understand what will traffic most likely look like on a Monday, on a Tuesday, on a Wednesday. So with historical data, you can pretty much try to model that there's a morning peak, so demand will rise in the morning as people go to work. Then it slows down a bit, then there's an evening peak, people going back home from work, and then it slows down throughout the night. And so with these two blocks, essentially, these are the tools for traffic engineers today to get the most likely traffic on a Monday, on a Tuesday, on a Wednesday, and then a depiction of what's happening today. And that's what's used by the system to control it. And then goes some optimization, because obviously accidents happen, weather disturbances happen, special events like ball games happen, and so the job of the traffic engineer is to make that process better. So you could view this as the dream situation of any traffic engineer is to have everything green. So that means somehow they figure out the magic way to sync up the traffic lights and everybody's flowing fast and nobody is stuck in traffic. That's obviously ideal. The reality is very different. But that's an aspiration that you could think about as someone optimizing the system. And to do that, there is an interface because even though there's a lot of science fiction movies where everything flows automatically, at the end of the day in the US and in many countries in the world, you still have humans in charge. If you've watched the movie The Italian Job, there's a traffic center that gets hacked. This is this traffic center, that's the LA traffic center, and there's two of them actually, because there's the state and there's the MPO in charge. And in that traffic center, it's just like an air traffic control center. There's lots of displays with traffic and people making decisions in semi-automated tools. And part of the jobs we do at Berkeley is to help the California DOT build these tools, decision support tools, that will provide better regulation, if you will, of traffic. And what that means is that in this interface, the operator cannot optimize in his or her head traffic online. So there is a database of playbooks, situations which are known, things which have been optimized offline, things which we know work. And what the human does is it selects semi-automatically in this database the playbook for today. Oh, we know it's a Friday, that Friday traffic. We know it's raining, and we know there's a rain closure, and we know that playbook number 37s work really well. Of course, that gets semi-automated, so things are pushed to the operator, or at least that's the dream. Things get pushed to the operator, so the operator can select the best way to make things flow. So this is, in a sense, the contribution of the last century. This last century has brought the automobile, has brought the traffic lights, has brought a lot of technology, and that's the way things work today. So what I'm going to do now is try to walk through some of the underlying tools that are under the hood. That'll bring us to maybe 2/3 of the talk. And in the last third of the talk, I'm going to explain how we have a Frankenstein on the loose and how everything I've spoken about before doesn't really work anymore, and that will be an explanation of why we have all these problems of traffic that become more and more hard to cope with, if you will. So first, one of the things which is interesting that has happened over the last 5 years is we have witnessed a complete revolution of demand forecast. 10 years ago, if you wanted to know where people are coming from and where they're working and how you can use that information to regulate traffic, essentially the only source of data you would have is people running census, knocking on your door every 10 years, asking you to fill a questionnaire, essentially answering question where your children go to school, where you work, where you shop, and based on that, they would build these models. And then with the explosion of smartphones, what has happened is that all of you probably in this room, or most of you in this room, have a phone. And even if you're not willing to disclose your precise location, the cell phone operator, AT&T, T-Mobile, Sprint, whoever you're using, has the knowledge of the cell tower you're talking to, just because your phone is connected to some cell tower. Which means if the access provider has enough of you, for example, AT&T has about 40% of the US population, or at least that's true in California, then that means that operator has the ability all the time, when your phone is on, to know which cell tower you're talking to, which gives a notion of your location within roughly 200 or 300 meters. And that's enough. It's not precise. I can't know exactly which block you're on or which street you're on, but that's enough to figure out large-scale mobility of traffic. And so what that means is that if you don't do math, you can skip this. If you do math, that's probably trivial. The point is that with convex optimization tools that are fairly common, you can find a least square estimate of the most likely place people live to the most likely place they go with that data. And Kathy Wu, who's sitting here, was one of the people who did that work. And so what it means in practical terms is like, that's what the data looks like. So this is for LA. And what you see in pink is an example of cell tower records of a person who is driving through LA. And it's not the precise location. You can see this little kink here. That's because the cell tower he's talking to happens to be off the main road. But from that, you can find the rough mobility pattern of that person. So thank you for all of you to contributing this data, because we all contribute to this database, so willingly or not, knowingly or not. But what's interesting here is that over the last 5 years, that data has become predominantly available to a lot of different agencies through various agreements they have with these data providers, which essentially enables transportation practitioners to model much more accurately the patterns of people. And you can see interesting things. Like, this is an example of a FedEx truck doing delivery. So it explains why that truck is throughout the day delivering to different locations. This is a person going to work, probably going to the bar or to the shopping mall or something, and then going home after the end of a hard day, and so on and so forth. And so the way these set of data are used nowadays is from this approximate set of location, which you have at a very high level and large scale, you can identify what's called origin-destination matrices, which are a way to encode where people live and where people work. And from that, with models, and that's part of the work we do in transportation engineering and in control and optimization, figure out the network loading, which is essentially if you know where people are, if you know where they work, and if you know an approximate routing, with good models, you should be able to somehow forecast to a certain degree of accuracy their routes. And so the type of results that you can extract from this is, given the density of cell towers, so some places like downtown Seattle have very high density, lots of cell towers. Some places which are rural have a less big density, with less cell towers. And based on the density of these towers, you can essentially determine the accuracy up to which you can go and with this type of demand. So that state and demand forecast, once you have it, if you have good statistical models, it's a very efficient tool for practitioners, because now you have a good way to forecast what's going to happen on a typical Friday when it's raining or when there's a bowl game. Now, another revolution that happened over the last 10 years, which all of us here benefited from, is the revolution of traffic estimation. And so that's the story I'll tell for the next few minutes. So state estimation is the process of taking data, whether you have cell phone data, loop data, detector data, a model, and finding the most likely state of traffic, given that the model is not perfect, the data is not perfect, and the truth is somewhere in the middle. And so the typical tool that transportation engineers use for this is this time-space diagram I was talking about before, which plots the time on the horizontal axis, the location on the freeway on the vertical axis. A certain color level indicates the congestion level, so 70 miles an hour is going to be blue and low speed is going to be red. And if you are able to reconstruct this all the time, then that means you have perfect vision of the speed of people everywhere on the network. And you do this for every link. And of course, it's not possible, but you can get as close as you can. And so part of the work we've been doing over the last 10 years is exactly the development of algorithms that enable the reconstruction of such time-space diagrams. And to show you how it works is, imagine you had none of this data, but that's what you're trying to reconstruct, so just keep this in the back of your mind. If you were able to sample data at given locations on the freeway, like a loop detector, that's essentially saying that you have access to the data along the black lines. And if they're interrupted, that means you have a sensor failure, so you don't have access for these particular times. If you were able to make an estimate that at midnight the freeway is nearly empty, that means you have knowledge of the data along the green line. If you were able to track some of you because, say, you're willing to share your data, that means you're able to sample the data along a trajectory. If you do environmental science, that's called a Lagrangian measurement. And that means you're able to measure that function along that line. And if you're just able to re-identify cars, like for example, you have an easy pass or fast track or a transponder, that means you're able to say, oh, the vehicle in this here is the same as the vehicle on that dot up there. So that's roughly the data that is available today. And so part of the work that we've been doing over the last 10 years, and that is, I think, a very mature now, is the process of developing algorithms so that if you have this type of data, you're able to reconstruct a picture. And to do that, what you use is you use mathematical models of traffic, which are represented here in the form of a partial differential equation. That's a Hamilton-Jacobi equation. And that's essentially this model of traffic. It's like this 50 years of work of transportation engineer leading to a model. And then, so that's what goes in this box. And then having that sensing data essentially say that you can sample the data at given location. You have initial conditions. You have value of the function along some trajectories and at specific points. And so part of the work of optimization engineers is essentially trying to find a mathematical formulation that is able to say that given the data I see, that is not perfect, given the model I have that is not perfect either, represented by these two polygons, my guess, resulting from the optimization of a convex program, is that the value of the system, the state of the system is this. And that's what these theorems say here. If you do partial differential equations, it says that you can optimize a least square problem under Hamilton-Jacobi constraint as a convex program. Otherwise, just think about it as given imperfect data, given an imperfect model, what is the truth? And the truth is somewhere in the middle. And so this is one of the things we've been working on for the last 10 years. And so let me show you how it works in practice. This is data which represents GPS tracks of 2% of traffic. So again, time-space diagram, time, location, and each dot is a GPS track of a car moving on the freeway, sending you their position every 3 seconds. And that represents about 2% of traffic here. And I'll explain later how that data was collected. So essentially what the algorithms do is they take that data and they are able to fill the data where there's no holes. So here, there is nearly no hole, so you can read traffic. But say I get rid of 99% of the data, that's what it looks like now, then if I ask my 5-year-old son or my 9-year-old daughter to kind of paint in between, they'll probably figure out the colors. But essentially what the algorithms do is that, except they do it mathematically. So they're able to reconstruct this from this, and this is the ground truth. And so this is a graphical way of explaining how the system works here. And so 10 years ago, when there was no phones, essentially there was no such data. Initially, people thought, well, with a few percent of data, can we reconstruct traffic? And it was not obvious then. And obviously today, reality is we all have traffic on our phones, and so this has become part of everybody's technology. And so it's interesting to see how this domain has matured over the years, because today it has become a commodity that everybody can get everywhere for free. And this has a lot of consequences that we'll talk about in the second part of the talk. So when we started the project, and Jeff was one of the early participants, so back in 2007, the iPhone 1 did not have a GPS. The smartphone of the moment was the Nokia, defunct brand, and the Android was not even born. And so what we did, and Jeff was one of the main architects of the first system, is we built the first traffic app that was ever deployed in North America to collect traffic from these phones, which look like a vintage object you want to collect today if you're into these kinds of things, but which was the smartphone of the moment. This was one of the first smartphones ever. And we deployed this app mostly in California, and were able to reconstruct what was one of the first traffic map ever built from mobile data. So within a few years, we managed to change this, which is a vintage website. Actually, if you go to California, they still have it up, and which was the only way you could get access to traffic in 2008 into this, which all of you have on your phone today. And so to do this, you have to replace yourself 10 years ago, where nobody really believed, and in particular, a lot of the DOTs didn't believe it could be done. So in order to prove to the DOT that it could be done, we had to first try it at small scale. So we ran an experiment called the Mobile Century experiment, in which we hired 100 students, actually 200 students, to drive 100 cars back and forth, 10 hours, on 10 miles of freeway. Very boring job. But the goal of that experiment was to prove that this traffic, which was about 2% of traffic, was enough to reconstruct traffic. And think again, nowadays you don't even dispute, you have it on your phone. But 10 years ago, it was not even clear it could be done. So we ran that experiment for 10 hours and collected enough data then to demonstrate that with this percentage of data, you would have good enough accuracy. This 2% number was not chosen by mistake. Companies then, including Google and Apple, thought that within 18 to 24 months of the experiment, that would be the penetration rate on US freeways, which obviously now is above 100%, but which then were really good forecasts. So when we ran the experiment, it was like a nice military operation back in my old days in the military, where we had a command center. Each car had this smartphone in it, and essentially we were running things out of a parking lot for the whole day, having a lot of TV crews there to film the experiment. We made practically every TV channel. An interesting side story is we were trying a lot of different video cameras on bridges to film the entire thing, and the student who was here, who was a faculty at UT Austin, who was running all the preliminary tests, went every day for a few weeks on the same bridge to try a different camera with different weather to make sure it would work. He was almost arrested by the police on the day because people were reporting terrorist activities on the bridge. So the police officer came to the bridge really upset and told him, what the hell are you doing here? And he said, oh, I'm working for UC Berkeley and Caltrans on this experiment. And the police person told him, okay, put a helmet on next time so it doesn't get people nervous. So the next day he puts a helmet on and nobody called. And so I guess the conclusion is if you want to do anything shifty on a bridge, as long as you wear the right equipment, you'll be fine. So we ran the experiment and had a press conference with the CTO of Nokia, who flew in from Helsinki on that day. This is what you would have seen from a helicopter if you had been above the experiment. Each of the dots here is a vehicle running that very first experiment. And while we were doing it, we essentially run a live view of traffic, and this is probably the first time ever in history that people could watch traffic collected exclusively from smartphones. Again, something that you have on your phones every day today, but which we managed to put online for 10 hours on 10 miles of freeway just to demonstrate it could be done. What you see here is in front of the press, people pointing on the display. Something they couldn't believe at the time is that around 10 o'clock in the morning, when traffic should have been smooth, we saw this gigantic piece of congestion, and we couldn't believe that there was a traffic jam there. So at that point, I realized that I was probably going to lose my job because the algorithm was not working well, and this would all be on live TV. That person used to work at Traffic.com, another defunct company, and what she's doing on that picture is actually calling Traffic.com because nobody would believe that was happening. And it turns out there was a 5-car pileup accident that we caught before the police. We know this because they had pagers, another defunct device, and the pagers all start to beep as soon as there's an accident. And so instantaneously it switched the mood with the TV crews there because they figured out, wow, that stuff is really cool. And the rumor since is that we did the accident on purpose to demonstrate the technology. And that rumor came from Stanford, another school in the Bay Area that we won't talk about. So now back to where we are today. We continued building the system. In fact, Jeff actually, I'll tell another story. I never tell that story, but since Jeff is here, we're going to end up 5 minutes late today, but this is a story I never tell. So when we ran that experiment, we had to build that system in about 4 weeks. And nobody knew how to program in Java except Jeff. So we asked Jeff to teach everybody how to program Java. And in a week, everybody was programming Java, but absolutely horribly. And so we put the program together. The last compilation of the code happened at 4 a.m., and the launch was at 10 a.m. that morning. A bunch of students were sleeping on the floor at Nokia headquarters, compiling. Finally, at 4 o'clock, we compiled the code. It seemed to be working. So we started the experiment at 10, and then Jeff was in the command center and making sure that nothing breaks. And then there's something called leaking memory. If you've programmed, you know about leaking memory. And essentially, that when memory leaks and leaks and leaks, at some point you saturate your memory and your computer crashes. And so I don't exactly know how this worked, but essentially there was so much leaking memory that every 45 minutes we had to reboot the system because the leaking memory problem. And so when we were giving that presentation in front of TV and then later at a seminar, I had no idea about this leaking memory problem. So Jeff was calling someone, I don't even know who it was, and someone was walking to me and like, hey, the system is going to crash in 3 minutes. You need to move in front of the screen while we reboot the system. And this was essentially every 5 minutes, every 45 minutes, Jeff was calling someone who was telling me, move in front of the screen, we're rebooting, and then continue the demo. And this is, so I never told that story before, but since Jeff, and I really should acknowledge the fact that, this was really Jeff's, so this was the first version. And, in engineering, you have to rebuild the system many times until it works well. And after a while, it worked well. So this is an example of what that data looks like. This is 500 taxis in the city of San Francisco. You can recognize it because it drops a GPS point every 30 seconds. So after a while, you can recognize the city. And that gives you a sense, like if you can collect data from 500 vehicles in a city like San Francisco, that's the scale of data you get. Now imagine the city of San Francisco today has 40,000 registered Uber drivers. And each of these Uber drivers, plus you if you ride an Uber, transmit one GPS point every 2 or 3 seconds, because that's how you see the car moving on your screen. So you can imagine this data, this was revolutionary 10 years ago. Maybe 9 or 8 years ago, it enabled traffic information. Today, there's so much data that this is almost a mature field. And so what companies like Apple, like Google, Waze, which are now the same, Inrix, have built is essentially traffic monitoring system, and they more or less all look the same. It's like there's a bunch of data feeds that are filtered, that feed models, like the one I've shown before, that produce estimates, that's what you get on your phone, that get transmitted to customers, whether you're using a phone, a web browser, or any other system. And that's the genesis of these systems. So a few years into the project, people were really trying to figure out, well, how well is that system working? And so in 2009, one of the things we were doing at the time is we were benchmarking ourselves against Google, because this was the beginning of the supremacy of Google Maps. And so the type of things we were looking at is, at the time, Google was not using smartphone data. And so we wanted to know how much faster than the state-of-the-art can this system be. So what you see on the left is a movie of, you'll see a movie of Google traffic. It's accelerated. One frame is 30 seconds, because watching traffic on the web is a very boring thing. And then on the right is the interface of the system we had built. And so what we were trying to demonstrate at the time is that essentially you can monitor traffic much faster. And so on the left, you see an accident happening. You'll see it in about 2 or 3 seconds. It's happening right now. And that will create a big shock wave in the back. And it took, at the time, Google about 15 minutes to show it on their display. And so this was what we were showing to kind of proselytize the public agency to say you should really start to invest in technology to ingest that data, because that is really the way traffic will be managed in the future. And so the project matured, and a lot of companies have hired our students since. The person running Apple traffic, Ryan Herring, was one of the co-creators of that system with Jeff. People at Google and many other companies are essentially took a lot of the things we did in the lab and migrated it to that to your phone. And so I think it's fair to say later, about 10 years later, that there's still a lot of research happening, because traffic predictions are not perfect. I've missed only one flight ever in my life because of bad traffic predictions. Maybe you have. You certainly have missed meetings. I have. But I think overall, this is a fairly mature field. And whether modeling contributions, estimation, experimental, or data quality contributions still need to be made, things have progressed quite well. So now the question is, we collectively have built this as a community. It's 2017. Where does that leave us? And so this goes into the more interesting part of the talk. Every morning or every day you're using Google Maps or any other your favorite apps. For example, if you want to go to from Berkeley to that other university I mentioned before on the other side of the bay, you punch your destination. That's my alma mater, by the way, so I'm a bit conflicted. So you punch your destination, it will give you the shortest path, and it probably will give you another 2 alternative paths, which usually are the same shortest time. That's the way these things work. Now, think about it for a minute. What does it do to the system? 10 years ago, you knew how to go to work. And since you had no information, you would roughly go to work the same route, because that's you knew how to do. But now, you have information. That means you have a feedback loop around you. And if that feedback loop tells you, don't take this route, take that one instead, you'll do it. So that means that technology that all of you have for free all the time, everywhere, your phone, enables you to have a feedback loop inside the system, and that's very bad. Imagine you're building an autopilot for a truck, but now you're transplanting the software onto a car. It's not meant for a car, it's meant for a truck. Or autopilot for an aircraft, on jet fighter, and then you put it on a 747. It doesn't work. Well, that's what's happening to traffic now. Now you could think, well, that's kind of an abstract way of thinking about it, but actually it's not. If you're trying to optimize a system, but you have a wrong model of the system because you have forgotten this feedback loop, things could go really wrong. And here's an example. So initially, people thought, oh, everybody has traffic information, and if we can get anybody the best route to their destination, that will make traffic flow better. And elected officials even made these statements in public. Don't want to finger point at people or organizations, but if you look on the web, you'll find tons of these. People assuming that if all of us have the most efficient route to our destination, we improve traffic. But then, sooner or later, people started to realize that something's wrong. And in fact, I'm just going to flip through these, but if you have noticed more traffic in your neighborhood recently, you're not alone. In fact, there's a lot of places where people have started to figure out, that's strange, there's a lot more traffic. And then they figured out, oh, yeah, that's because there's popular apps, and it turns out that these apps are running more and more people through my neighborhood. So if you have seen that happening, well, that's a very known phenomenon. Then people started to get really upset. So they started to resist. So first they did funny things like posting signs, you should be ashamed to come to my neighborhood. Then they started to do funnier things like posting fake detour signs to confuse people going through their neighborhoods. There's even manuals on how to spoof and confuse people using these apps. And then cities started to get involved and organized. So for example, what they did is they started to build more street bumps. Because if you build street bumps or stop signs, traffic slows down. So by screwing your own traffic, you're making everybody's life more miserable, but then people avoid your neighborhood. This is a reality of urban planning, so there's other ways to do it. You could turn restrictions. You could start switching the traffic lights in your neighborhood to make sure that it's taking more and more time to drive through your neighborhood. And so it's an interesting situation in which urban planners today have found no better way to resist than making it harder to drive through their own neighborhoods. So this is why I mentioned Frankenstein at the beginning, because we collectively built that routing engine that is free, that all can use, and now, because the residential streets are not meant to support all that traffic, we're in a situation where people are trying to make traffic worse so that people stay out of their neighborhood. And that war went on and on. That war is still happening to the point that elected officials are now trying to figure out how to solve the problem. And the bad news is there is no easy solution to that problem. At some point, people even thought that citizens would start to sue Waze, and ironically, Waze, which is one of the leading companies in this field, which was born in Israel, even saw the first lawsuit in Israel. So it's ironic that the first lawsuit happened where the company was born. And it's probably only a matter of time before we see class actions in the US. So now we should ask ourselves, what have we done, right? We have given everybody that free information, the ability to be more efficient, but somehow it has made things worse. And this is a widespread phenomenon. For example, what you can see here is a map of the places where this has hit the news. I mean, if it's bad enough that it hits the news, that means there's a lot of other places where it's happening. If you have issues in your neighborhood, please email us, because we are trying to inventory. This is like cancer. It's like it's growing, it's everywhere. And we'd like to understand what's happening. So now that this has become a problem that is, a very severe problem, people have started to figure out, well, can we explain it? Can we understand it? So, because if you understand it, maybe you can fix it. So let me explain, let me show you why this is happening, and then you'll understand the complexity of sharing information of that nature to drivers, because there's no easy fix. The movie you're about to see has twice the same simulation. The bottom part is, I guess, 10 years ago when nobody had that information, and the upper part is, let's say, 20% of the people, you, or using the same app, whether using Waze or Google or Apple or Inrix or anything you want. And then here's what happens when you give people information. So this is a simulation. So let's say there is an accident that blocks 3 lanes. That creates a big traffic accident, so traffic jam happens. I'm sure you've all been in a traffic jam before. But if you give people information, then people want to leave the freeway immediately, because that's what the app tells you to do. If you don't give people the information, they stay on the freeway. Ultimately, the freeway gets cleared, and things start flushing. If you have given people the information, once the freeway is being flushed out, now you have a lot of people, hundreds of people, on the off-ramp. So that has a lot of interesting consequences. First, it creates more traffic, because everyone wants to leave the freeway at the same time. It's not meant to be that way. So now you have a ton of traffic on the freeway because people have that information. And then, so that's you. Even in that process, in trying to make traffic on the freeway better, you've made traffic on the freeway worse. But then, in addition, now you have these hundreds of people on the side streets, which are absolutely not meant to support that traffic either. First, because they're small, and second, because they have a ton of traffic lights, which are not meant to process as much traffic. So now you've made that traffic much worse also. And this is a reality of traffic information today. This is why you see a lot more traffic in your neighborhood, and this is why your neighborhood is suffering from it, because it's not meant to support that extra traffic. So these simple things, which all in isolation can be understood and have been studied by generations and generations of traffic engineers, when they all become coupled because of that information system, then they become problematic. So people understand bottlenecks, people understand rerouting, people understand bottleneck removal, people understand residual congestion routing, but all of these sequenced together is what's causing the problem. And so this is where analysis really should enable us to at least understand that problem. And the good news is there is a good theory that can explain this, and that theory is game theory. So what's happening here is that at the inner loop of this feedback system, people are inherently behaving selfishly. In the morning, when you punch your destination on your phone, what you want is you want to go to work as fast as possible. So you want selfishly what's best for you. And there's no other, I mean, I don't blame you, I do the same. And the point is, this is a feature of traffic. You wouldn't want to take a 10 or 20 minutes detour for the greater good of society. You want to go to your work, you want to go to whatever you have to do. So if you model this, there's many models that have been developed over the years to encompass that system, and there's a very famous concept in economics called the Nash equilibrium, which can characterize this. So I'm going to just skip this, but explain it on a very simple example. Say you go from here to here, and 10 years ago you had no information. There's no reason why you would leave the freeway, even if there is traffic, because first, you don't know the neighborhood, second, maybe it's dangerous, third, you've never done it before, so most of the people would just stay on the freeway, which means essentially you'd have a ton of travel time on that freeway, and then nobody would go to these side streets. And then as more and more and more people have that information, then more and more people would figure out, oh, I have an alternative. And people will clog that street, and when that street gets clogged, then people will see the map and say, oh, this one is actually better, and they'll start to clog that street. And so if you try to compute the travel time as more and more people use the app, that's what it looks like. So you can think of this as 10 years ago, when nobody had the information, travel time on the freeway was terrible, travel time in Pasadena was awesome, and so everybody stayed on the freeway, and that's the way things were 10 years ago. And then today, maybe 20% of the population use the app. So in the meantime, as more and more and more people use the app, then they clog the first street, and they clog the second street, and finally travel time became the same. It's equally bad whether you're on the freeway or whether you're on the arterial roads. That's called the Nash equilibrium. If you've taken any economics class, that's probably something you've seen before. If you've seen the movie A Beautiful Mind, that's the story of John Nash. And the reason why he got the Nobel Prize for this is because if everybody behaves selfishly in this way, that means there's no incentive to change your behavior, then one can prove that, at least in the case of transportation, that's not optimal. That means that if all of us use what we think is the shortest path to go to work, it actually leads to a worse outcome than if we were all collaboratively working together. And that's why all these headlines that you see of mayor of this city teams up with that company to improve traffic by giving you best information for traffic is just complete wrong economically, but it also is demonstrated in practice. And so the sad situation of sharing that traffic information is that today, by giving people better traffic information, we are actually making the system worse because of that Nash equilibrium problem we see here. And there is something called the price of anarchy, which is essentially how much worse is that Nash equilibrium than if everybody was collaborating. And that price of anarchy is a measure of how bad the system is. And so part of the work that we are going to do in the future is understanding what are the proper structure and mechanisms that one should use to fix that problem. The problem, so I'm going to skip a lot of the mathematics here, but I think to try to understand the problem, it's really a two-layer problem. The first layer problem is that we all want what's best for ourselves. We all want the shortest path or the fastest path to go to work. So the point is we're not going to collaborate by sending people on a longer route for the greater good of society. And then at the higher level, there's absolutely no incentives for companies either to do the same. If I'm Google, and if I'm giving you a travel time, my incentive as Google is to give you the best for you, because if I give you something better for society that puts you on a longer path, the first thing you're going to do is delete the app on your phone and try another app. And that's a reality. So these apps are not going to collaborate with each other either for the same reason. And so what you end up with is a situation in which not only you have a feedback loop, but you have a set of different feedback loops that are not clear to understand either. Like some of you use Google, some of you use Waze, that's nearly the same nowadays. Some use Apple, some use INRIX. All of them have a slightly different algorithm that tries to give you what's best for you. And so I think the game over the next 10 years is to try to understand what kind of control mechanisms can be happening at this level, which is the level of regulation, to fix that problem. And there's probably another 10 years of work. And that problem is even harder because that's happening one day. But the truth is, if you think about Google today, if you think about Google 6 months ago, if you think about Google 2 years ago, or whatever app you're using, this also changes. You probably noticed Google or any of these apps push you different routes, push you different alternatives. That's because the algorithm itself is learning over time. So in addition to that problem, which up to now has been described in a pretty static manner, it turns out that this is also a learning dynamics. The system over time itself learns. And if you don't understand that second dynamics, that makes it even harder to control the system. And so part of the work we do consists in understanding how do these algorithms learn over time? Because if we have at least a good understanding of the way they learn, then we could say something about what they converge to. And so in game theoretical terms, that means that if I am a routing app, every day, essentially, I route a bunch of users. I look at how well I did, because I can tell how fast they took. I can compare them. That's what's happening probably under the hood at all these apps. And then the next day, the algorithm changes based on the data. So part of the work we're doing now is trying to understand if we can make assumptions on the way these apps learn, can we say anything about what it is going to converge to? And so that field is called repeated games. And depending on the assumptions you make on the games that these apps are playing, what you can prove is that in some cases, at best, they converge to a Nash equilibrium. And in some cases, they don't even converge. That means if not used properly at super large scale, you could have really bad situations where on Monday, apps route everybody on one freeway. On Tuesday, next freeway, because the first freeway was terrible, and things could get really unstable. And these are things that you can start to see already happening. And so part of the theoretical work we do consists in trying to prove that at least for certain learning mechanisms, so you can think about it as a machine learning algorithm that runs all the statistics on the collected data, and if you, depending on the assumption you make on the learning, which happens inside these apps, you could at least make some guarantees that if some conditions are satisfied, this is not going to converge to something bad, and if possible, this could converge to something better. And so part of understanding that behavior essentially amounts to characterizing a Nash equilibrium and showing that at least in some cases, the system converges to a Nash equilibrium. So if you make almost no assumption on this system and assume that the algorithm used by these apps are no-regret algorithms, which are very general class of algorithms, then you can't even prove convergence. You can only prove convergence on average. If you assume that these apps work a little bit more closer to the hedge algorithm, which is a very commonly known algorithm in finance, then at least you can show that the apps converge almost surely to a Nash equilibrium. That's not great news, but that's still better. And then if you make the assumption that these algorithms learn using a mirror descent step, which is now much closer to a concept commonly used in convex optimization, then you can prove not only convergence to Nash equilibrium, but you can also have a rate of convergence. And I'm going to skip the details of the proofs here, but I'm happy to keep that for the end. So the point is that if you view the system as some environment which evolves, some agents which are routed by this algorithm, depending on the way the algorithms are trained, you can prove that the system will be steered to different types of equilibria. And that's really the beginning of something which is very important in the future, because we're going to see a lot more regulation of traffic. It's just unavoidable. If you look at the way Silicon Valley is asphyxiated, when I was a student at that university in the south of the Bay, the commute time between San Francisco and Cupertino was about 45 minutes. Nowadays, it's about 1 hour 20. So there is no choice. At some point, regulation will kick in. But to understand that regulation, we really have to think hierarchically about this matryoshka problem. At the core is you, who have the need for the fastest route. So that means you're regulating a system which is part of a much broader control scheme, which itself will keep changing every day as the algorithms that are routing you learn. And that's a reality of urban planning, and that goes maybe back to the spirit of the Wank lecture, that technology should really inform policy. These are problems which are reality and will become more and more crucial. The smartphone explosion, that's the story of the last 10 years. The fact that 10 years ago, probably nobody had a smartphone, now everybody has a smartphone. But then if you think about demographic growth, which is very true for Seattle and certainly crucial in California, that's going to only make things worse. And then, in addition to this, if you think about perturbations of the system which are local, there was a startup called Google when I was a student at Stanford, which had 10 people. Now Google's campus in Mountain View probably has 30 or 40,000 people. A few years ago, there was a company named Tesla that made electric cars. Today, the Tesla factory in the south of the Bay has a couple thousand people. In 3 years, Treasure Island will have 18,000 additional apartments that will be open for the public. You can imagine what they will do to the bridge. And so understanding what these perturbations of the system do as the algorithm learn is going to be essential to regulate traffic better. And so the reason why these problems are difficult is because at the core of these problems, you have dynamics which are inherently complex. The way people route themselves, the way people drive, the way traffic behaves, it's fairly underlying nonlinear dynamics are quite hard to understand. It's also distributed and decentralized. The way control is done is not that easy. You have non-cooperative players. There's no reason why you would sacrifice your travel time to help society. People want to go to work as fast as they can. And you have humans in the loop, which also induce additional difficulties. And so understanding all these complex loops in this game theoretical framework is going to be one of the first steps towards at least understanding the problem. Fixing the problem is even harder, because now even if you knew that you should send 20% of your commuters a different route to improve traffic, I mean, how do you do it? Do you pay people? Do you give people the free cappuccino to take a 20 minutes detour? That probably is not likely to work. You could prevent people from entering the freeway by making it sure that you cannot let a car with less than 5 people onto that lane, and that's a potential alternative. And there are several other ways to do this. But even when we understand this, which is not happening tomorrow, even when we understand this, once we understand it, how to actually do something about it is something which is even harder to conceive, and that's something where a lot of work is going to be needed, and that work will be needed essentially in an area which is kind of in the middle of technology and policy, and that's one of the areas that we're very excited to work on at Berkeley. So to finish, in the last 2 or 3 minutes, I also would like to talk about a few other mobile sensor problems that we've been working on, which are paramount to civil engineering. In fact, one of the first apps we worked on when I joined the faculty 10 years ago was iShake. iShake was one of the first traffic apps to monitor earthquakes using smartphones. Another beauty of the smartphones is that they have accelerometers. And so one of the things we did initially is try to see if you put, this is a shake table that's to replicate earthquake when you built models if you're not a structural engineer. So we tried a bunch of smartphones on shake tables and try to see how good a measurement you would get and would that enable us to measure earthquakes. And it turned out that worked quite well. So the SciSmall app took this, and today T-Mobile has an app which can be used to monitor earthquakes using smartphones. Another thing which we were also very excited about is, this is, it goes just so a phone that shakes. We just spoke about phones that drive. That's a phone that swims. One of the things we did initially when we started that mobile sensing program is try to understand how we could use mobile phones in floaters to monitor water quality and river motion. California has a lot of water problems, as you know. And so we built these 100 floating sensors that have essentially propellers and can measure things, and then deployed them in the Sacramento Delta. So watching traffic and watching water is also equally boring, so this is why the movie is accelerated. But so they don't swim as fast as you can see in the movie, but the point here is that they can readjust themselves and float along the river, transmit their data so that we can reconstruct water river flow in real time. And then maybe one of the last mobile sensing problems we have started to work on recently, you can see that the theme is really always try to use mobile measurements to reconstruct something, is there's a problem that is really dear to a lot of our members in our group, because a lot of us have had families affected by Alzheimer's disease. And so we try to instrument patients with Alzheimer's disease to see if we could monitor falls. And we thought smartwatches was going to be the next thing. And it turned out to really not work well. But one thing we've managed to do today with video cameras is that using deep learning, so we deploy, this is an Alzheimer patient in a memory care facility we're operating in California. Using deep learning and video camera networks, we're actually able not only to detect when people fall, so the level of color here, red, indicates the algorithm has detected this patient is fallen down, but also we are able to start to collect enough data to predict when people will fall. And it's interesting because in these type of situations, you can see that a fall is about to happen by the way the person walks or by the way the person interacts. And so what we really hope with this is to be able to reduce the number of falls in memory care facilities by a lot of different techniques that we're working on with occupational therapists. So we've come a long way from mobile phones to be used for traffic, which is still kind of the core of what our group does, to a lot of different applications, and healthcare is one that is of particular interest. So with this, I'd like to stop. I again would like to thank the University of Washington for inviting me for this lecture, the Wang family for the generous endowment, Jeff for being my host, and if we have time, I'd love to answer any questions you have. Thank you.